All right, so this is the homework problem in the car. I don't have any of the slides set up this time, but hopefully we can make it through. So we have the car traveling at 20 meters per second, call it that way, and it ends up taking about 50 meters to stop. And by the end of that, obviously it's going 0 meters per second. And then we have some other information, like the fact that there's like this seat rest, and on top of the seat rest, there's a spider. We're trying to find out whether the spider is going to end up on top of the person's head. So there's a few steps to going through and solving this. Oh, we also have the coefficient of static friction is equal to 0.5. The coefficient of kinetic friction is equal to 0.3. So we're trying to figure out whether it will slide off onto your head or not. And I'll tell you right now, we can already eliminate that kinetic friction constant, because the minute that we're going to end up using the kinetic friction constant, we know that we're already getting the spider on our head. So this is really a static problem. Either static's enough to keep it going, or sooner or later that spider's on your head. So we're going to start going through this, and there's actually two pieces to this problem. First off, we're going to find out how much force is on the spider. Like, this is the force that's actually slowing the spider down. And then we're going to find out the maximum frictional force. And we're going to compare those two numbers to see whether the spider ends up on somebody's head or not. So to figure out whether the force that's actually on the spider, we can look at this as a kinematics problem. We can say that right now we have some speed stuff, some distance stuff. So this is starting to look a lot like this equation here. V squared equals V naught squared plus 2a delta x. And then we're going to try and find out what acceleration is in this. We know that the final speed of it is 0. So this is going to work out to be something like negative V naught squared divided by 2 delta x is equal to the acceleration. But we have one other equation that we know acceleration is equal to. We know that acceleration is equal to the sum of the forces over the mass. So I can kind of combine these two equations together and say negative V naught squared over 2 delta x is equal to the sum of the forces over the mass. But there's really only one force that's on it. It's going to be the force of friction. That's the only thing that would keep the spider on the headrest as you stop. There's normal and gravity acting on it, but those are in the wrong directions to decelerate it. So we can work that out, and it does something to the effect of, when we clean that all up, the force of friction is going to be equal to, negative mv naught squared all over 2 delta x. So we can plug in the numbers that we have from this problem. I know that I have negative, the mass of the spider. Oh, I haven't written that out on the screen yet. It's 0.05. 0.05 kilograms times the speed that they're traveling, 20 squared, all over 2 times 50. And when we work all of that out, it works out to be 0.2 newtons. Okay, so that's how much force we need friction to be. Otherwise, the spider starts sliding. So to figure out how much friction there actually is, this is pretty easy. We can just say the force of friction is equal to mu times normal force. And because it's in vertical equilibrium, it's not moving up or down, that means normal force equals the force of gravity. So then I can just plug in all this junk, 0.05 and 10, and that works out to be a total of 0.25 newtons. Now remember, with friction, this number right here is the maximum. It's not how much friction there actually is. That's the most friction that the spider and the headrest could ever have. In reality, it's 0.2, because that's all it needs to be to keep that spider from moving. But, and the story is, yes, the spider stays put. It stays, the available frictional force is up to 0.25. We only needed 0.2, so it stays there. It does actually later on just voluntarily climb onto your head, and then it climbs down your back and it follows you home until, as you go to sleep, it wraps you up in spider webs and injects its like paralyzing venom into you, and it lays eggs, and the eggs like hatch inside of you, and then they live on you while you're paralyzed and slowly getting eaten and all those kind of things. But that's outside of this problem. So that's it. That's all you need to know. Hopefully this helped. Maybe I should cut that whole part about the spider. Oh well.